Hello everyone, my name is Robert and this is Lab 4. So the purpose of this lab is to explore the interaction of a falling magnet within a tube of aluminum foil and compare the results to a computation model using Faraday's law. For this we used two models. We first had, of course, our aluminum foil 2 model, which we passed the magnet through, and then later on we use a VPython glow script simulation. The results for this lab came out to be 2.1 seconds experimentally, and the simulation was around 2.5, so a little bit larger. So the fundamental principles used for this lab is, of course, Faraday's law, which is relating the time differential of the magnetic flux to the EMF. We're using PHYS law of magnetic field, and from that we are deriving the off-axis of a dipole for the magnetic field. And lastly, to calculate the speed and rate and position of the magnet as it passed through the tube in our simulation, we use Newton's second law to computationally update each position. So for the experimental portion, I defined the system as the magnet and the aluminum foil and the surroundings as the earth. I marked the magnetic pole using the magnetometer app from Lab 3. And then to calculate the time for it to pass through the aluminum foil, I did it from center to center as it passed through. I just put it into iMovie and averaged the time between each take, so I did it 5 times, and the average time was about 2.1 seconds for it to pass through center to center. Moving on to the computational model, the same initial conditions were set. I weighed the mass of the magnet itself on a triple beam balance, which gave me 0.0241 kilograms, and for the magnetic moment, I took that from Lab 3, which we measured to be 3.85. Also taking the measurements of the aluminum roll itself, it was 1 foot in length. The width was about 0.7 centimeters, and the inner radius as given. Add those together to give us the internal radius of the aluminum foil. Before the simulation loop, we defined 2 functions, the first function being the dipole off-axis magnetic field, which is given from the equation from PHYS of the mu naught over 4 pi 3 times mu dot r hat times r hat minus mu all over the r vector magnitude cubed as defined in the function. And then the second function calculates the time derivative of magnetic flux, which is the same as the magnitude of EMF, which we later use to calculate the current for each ring. And that one was given from the pre-lab for EMF equals the time derivative, which is equal to 3/2 mu naught times the magnetic moment times the distance y times speed times the r vector squared all over r squared plus the distance y squared to the 5/2. Within the simulation loop, the goal here was to calculate the magnetic force first, and then apply that using Newton's second of iterating through the change in force, the change in velocity, and the change in distance. So for here, the F loop, or the force on the loop, is derived from the magnetic force, and using the off-axis dipole magnetic field gives us the current times 2 pi r times the magnetic field times sine theta. And then to get the F net, we know that the 2 forces are going to be the magnetic force and the gravitational force, so add these together with gravity in the negative y direction should give us F net. And then walking through Newton's second, iterating through velocity and then position, and we can see that in the diagram we have an equal force as it's moving at constant velocity, F net equals 0, between the magnetic force and the gravitational. And as the magnet is falling, we can see the 2 different positions of the induced currents, with red being the counterclockwise current that's resisting its motion, and then the clockwise motion in blue. So to answer the 2 what-if questions, if the resistivity of the material was as close as possible to 0, it would serve as a better conductor and therefore have a greater induced current as there's less resistance against the induced EMF. And if there's holes in the aluminum foil, then the magnet would accelerate through those sections as there's no generated ring of current that would balance F net, and therefore it would accelerate faster. and not be at a constant velocity at that section.